Okay. For people just joining the video, I'm talking about something I said wrong a few lectures ago. So we were talking about glucose going to acetyl-CoA, and that acetyl-CoA is like the thing that we want to be producing. And I mentioned how if you're comparing like carbohydrate metabolism to fat metabolism, you can kind of count your carbons and figure out how many acetyl-CoAs you can make, and then it makes sense how much energy you can get out of it, because acetyl-CoA is sort of the thing that goes into the citric acid cycle, yada yada yada. And I mentioned like, glucose has 6 carbons, and acetyl-CoA has 2. So you get 3, but then someone pointed out that that's incorrect, which is correct of them to point out that was incorrect, because pyruvate has 3 carbons. So again, glucose 6 carbons, forget this, whatever. What I left out in my head and in the lecture is this, that when pyruvate gets converted to acetyl-CoA, you lose a carbon to carbon dioxide. So you get 2 acetyl-CoAs per glucose. My apologies. Yeah, so I'm going to go through the lecture as per usual, and then if we have time at the end, you guys can ask any questions for the exam. I would encourage you to ask them out loud in front of the class, because usually if one person emails me about something, a few people email me about something, and then it can go on the video, and everyone will get the benefit of your excellent questions. So there are no stupid questions. I'm going to put a sign up in my office that says that. Okay, we all cool? Okay, cardiovascular fit. So I was super pumped about this, but I got a horrible sleep last night, so I feel like I'm going to like temper my activity levels if anyone was bracing themselves for me to get super pumped about this. But I will say that cardiovascular phys is like my jam, and these will be my favorite lectures. So you got me for 4 in a row, and we're going to have a great time. I'll have a great time. I don't know if you guys will. Okay, so first I'm just going to go back over some of the stuff that Dennis talked about the last 2 days. So first of all, we have the flow model, which applies to mass and heat. And here's a nice summary that Dennis put together for you guys. Basically, asking the question of how flow can increase within the body. So, and this applies, as he was saying in the last 2 lectures, to everything. So muscle blood flow, so this is obviously blood flow through a muscle bed, the conductance of oxygen from the lungs to the blood, from the blood to the cell. And this is actually the reason that I like physiology, because a lot of these principles that you learn apply to lots of different pathways, so you don't have to memorize stuff in physiology. It's nice for us simple people who don't like memorizing stuff. So if you want to increase flow anywhere, you can increase your high energy side of things. So in terms of blood flow, this will be increasing arterial pressure. That's what's driving blood flow through a muscle, so you can increase arterial pressure. Again, in the case of diffusive conductance, you can increase the alveolar oxygen if you want to go from the lungs to the blood, etc., etc. So increasing the high energy component so as to increase the energy gradient. Conversely, you can decrease the low energy component. Are you guys all cool with this, or should I use my coffee analogy again? You guys are good, right? Okay. So again, this is just another way of increasing the energy gradient by reducing the low energy component. Or you can increase conductance. So again, when we're talking about blood flow through a vascular bed, that's vasodilating all of those arteries. So if you do all of these things, so increase the high energy component, decrease the low energy, and increase conductance, and you're going to have a massive increase in flow. But you'll get it, provided everything, like 2 of the things stay the same. If you increase 1, you'll get an increase in flow. Oh wait, sorry. 1, 2, 3. Any questions? Because that will be important to understanding what we're going to talk about today. Okay, so we also talked about, sorry, there's 2 more summary slides, this one, another one. The conservation of mass model. We're talking about flow into and out of a defined compartment of volume is determined by the mass and heat flow model, which we just covered. So changes in the volume or concentration of a substance in a defined compartment occurs when there's an imbalance between inflow and outflow. So the nice thing about our human bodies is like they're a certain size. So during exercise, training, that kind of thing, we can have adaptations, but we're always constrained by the size of things, so it kind of, again, makes things easier for dumb people like me who don't want to memorize stuff. So we're talking about blood volume. Like, again, you have a certain volume of blood vessels, certain volume of blood that can change with time, but at any given moment, this is going to be non-changeable. Oh, look, really went off the rails there. Okay, so, I don't know. Changes in the volume will occur when there's an imbalance between the inflow and the outflow. So, again, I think we're kind of beating a dead horse here, but increasing outflow relative to inflow obviously will decrease the volume concentration and will, again, increase the energy gradients. This is just what we were just saying. You increase the outflow, you lowered that low energy side of things, and you've got a bigger energy gradient. And then flow will eventually increase to equal the new outflow, but at a stable and reduced compartment volume. Does that make sense? We're letting whatever water out in this example. And then conversely, if we fix outflow and increase inflow, we're going to increase the volume here, and this is going to increase pressure. And again, reduce the energy gradient because we decreased that high component. Okay. Last thing, I think this is probably the most intuitive, at least to me. So elastic recoil, compliance, stretchiness, for a nice synonym, is the change in volume over the change in pressure. I think the nice way to think about this is with the balloon. Beautiful picture that I think Dennis made for you guys here. That obviously, if you've ever like blown up a balloon, you know when you're blowing up birthday balloons for a birthday girl, and like all of a sudden you get a real stiff one and you're just like hauling away on it. So you have to give more pressure to fill that balloon because it, for whatever reason, is a less compliant balloon. So again, you've got that really easy balloon to blow up, which is a compliant elastic structure versus the really hard one, a non-compliant. You need a greater change in pressure, and then you get dizzy from blowing up all the balloons. We actually reused her balloons because it was my other grad student's birthday, so sorry, I didn't blow you up balloons. But anyway, okay. Let's make it real interesting now. Get into cardiovascular phys. Okay, so this is kind of what I was saying before. What we have here is a closed loop design because ideally, none of your blood vessels are open. If they're open, it's problematic. So we know that we've got the heart, which is the pump that creates that pressure necessary to move blood through the circulatory system. The arterial circulation, so these are low resistance, high conductance tubes to conduct blood from the heart, specifically the left side of the heart. Left side of the heart goes to the systemic circulation, right to the pulmonary, to various organs. Microcirculation, so arterioles are the smaller tubes that are high resistance, low conductance. Capillaries, this is where the exchange occurs, so really thin vessels. Venules heading out from the capillaries. And then the systemic venous circulation, so low resistance, high conductance tubes. So really, like the systemic arterial and venous circulation, these are conduit tubes. We're just trying to get blood from here to here. So they're low resistance. The goal is not to control blood flow necessarily at this point. The control is just to get it here to here. And where we can really affect our blood flow is at the level of the arterioles and a little bit of the venules. So where we can get these really high resistance blood vessels. And actually, these are the blood vessels that we study in our lab. Okay. So arterial blood pressure is the force exerted by the blood against the arterial walls, and is determined by cardiac output and total vascular conductance. So anytime you get your blood pressure taken, we're talking about how much blood is there. So we're going back to those models at the beginning, and how much of that blood is pushing against the sides of the blood vessels. So you can picture like a really full balloon. But again, if you go back to our stretchy balloon versus our non-stretchy balloon, if you put the exact same amount of water into each, you're going to have more pressure inside the really stiff balloon than the really stretchy balloon. So the amount of the blood pushing against the sides of these blood vessels and the amount of compliance and resistance there is going to determine your blood pressure. Sorry, I'm going to be clicking ahead here. So systolic blood pressure is the pressure generated during ventricular systole, so the heart pumps, that's systole, that's your high number. So the heart pumps, that blood goes out into the aorta, and you get a surge of pressure. Diastolic is during ventricular relaxation, so your heart pumps, you get that surge of blood flow through, and then what you get with the blood vessels is, because they're stretchy, like your aorta is super stretchy, so it stretches to accommodate that increase in blood flow. If you get a really, we'll probably talk about this later, but if you get a really high systolic blood pressure, it's because your vessels are really stiff and they can't buffer that. So when you picture like a balloon expanding, it's really keeping the pressure constant inside that balloon, or at least decreasing the amount of pressure. If you have a really stiff balloon, or I don't know, I'm losing my analogy here, but it might pop because the pressure keeps on building and building and building. The stretchiness of the balloon walls can't sustain that pressure. So again, if they're really stretchy, they'll expand. If they're not stretchy, they'll go like this, and then all of a sudden the pressure builds and they pop. So anyway, so someone with really high systolic blood pressure means they have really non-compliant arteries. You young people will have really compliant arteries. Me, less so. This gets like worse and worse as you get older, which is a real bummer. But your blood vessels, so one of your guys' aorta, Yasmin's aorta might just expand whenever your heart, well, they definitely are expanding whenever your heart pumps. Mine probably expands, sadly, a little bit less, so I would have a higher systolic during the pumping of that heart, during systole. Diastole, so the heart relaxes, it comes down. If you had a lot of compliance in those arteries, you've got this like kind of recoil back down to maintain pressure nicely over the cardiac cycle, so it's not just a super big hit at systole and then really low diastole. That's not good. But your pressure will come down during diastole because the heart's not pumping into the blood vessels. And then mean arterial pressure is the mean. So they always teach you guys like 1/3 systolic plus 2/3 diastolic, I think, right? In our lab, actually, we just measure it constantly and then just take the mean of the blood pressure over the whole cardiac cycle. So it's both. The 1/3 plus 2/3 is if you're taking someone's manual blood pressure and you're like, hey, you're 120/80, then you can calculate their mean pressure from that. But in the lab, we just put a thing on their finger and measure it. We might be doing that in a lab. I don't know. We'll find out together. So you can calculate mean arterial pressure if you've got cardiac output and total vascular conductance. So it's cardiac output divided by conductance. You guys all know cardiac output, right? Heart rate times stroke volume. Is this new to anyone? Yeah, okay, good. And total vascular conductance is the inverse of resistance, so it's 1 over resistance. So conductance through a vascular bed, for instance, is how much blood is allowed to flow through. The resistance, and we'll cover this in I think maybe the next slide. Oh, no, this slide. Has to do with how much the vessels are trying to impair blood flow through a vessel. So if you want to increase conductance, you need to decrease resistance because they're the inverse of each other. And the way to change resistance is through these variables. So if we're talking about a certain vascular bed, let's say you're talking about your lower leg. That's what we do in the lab. This is an inside joke. It's not even a good inside joke. It's a terrible joke. Okay. So the length of the blood vessels are not going to change. They might if you're like growing, but presumably you guys are all done growing. So that's going to stay the same. Viscosity of the blood, that's really fascinating. We usually ignore that in my studies because it's not super easy to quantify, but viscosity, so you guys know what viscosity is, how thick the blood is. So if you have more red blood cells / less plasma volume relative to each other, you'll have an increase in viscosity. And then here's our big boy here, which is radius. And probably everyone has emphasized this to you, but I will continue to emphasize to you that the fact that there is a, oh no, to the power of 4, I almost forgot what that was called, is important because a very small change in radius ends up having a very big impact in vascular resistance. So the thing that we study actually in our lab is the means by which the sympathetic nervous system controls resistance. So sympathetic nervous system, again, sorry, I'm jumping ahead a little bit, but will fire on your resistance vessels, so those arterioles, and it's causing the vascular smooth muscle that surrounds those arterioles to constrict causing a change in radius, a decrease in radius. And a very small decrease in radius will cause a proportionately very big increase in resistance, and thus a big change in mean arterial pressure, in theory. You're a man. That's not on the exam. That's just me saying that. That's what I researched. Anyone have any questions about this? I just realized I'm not done this slide yet. I really stepped on my toes here. So blood pressure, MAP, mean arterial pressure, is the average pressure during a cardiac cycle, and it determines the rate of blood flow through the systemic circulation. So you guys know, you start exercising, what happens to your heart rate? It goes up, right? So your cardiac output's going up. So this is the body's way of increasing that high energy component that Dennis was talking about with the mass. Oh, right here, sorry, the flow model. Oh my God, I should just read ahead. Okay, so that is, you're increasing the high energy pressure so that you can increase blood flow. And that's why your heart rate increases during exercise, or one of the main reasons, to provide this increased drive so that you can increase conductance through the vascular bed. Does that make sense? Okay. So this is all relating it back to Dennis's model. How do you guys feel about, not Dennis's model, the model that Dennis told you guys? He didn't make it up. I don't think he made it up. Are you guys enjoying that, or are you kind of like, why am I learning this right now? You can tell me. I guess it's on camera. He doesn't listen back. Because basically, I think like when you learn at the beginning, you're kind of like, okay, I don't know. This seems like a lot of whatever, mumbo jumbo with like, but it really does help you, so you don't have to, again, like memorize stuff from like unit to unit. Now, like if you understand those things, it's going to make it a lot easier to understand cardiovascular. And if you sit down at the exam and we ask you, obviously not the midterm because this is not on the midterm, but if we ask you a question about cardiovascular and you're like, oh crap, I have no idea. In theory, you should be able to sit down, think about it. You're probably already sitting down, but in theory, you should be able to sit and think about it and figure it out based on these models because they all like make sense. So make sure you like get those 2 lectures, and if you don't, go find someone to help you. I can help you. Go find someone. I'm right here. Okay. All right, so again, we've kind of been talking about this, but the compartment for blood pressure, cardiac output, these relationships are the systemic and conduit arteries. Again, those can like, over time, you can create new blood vessels, angiogenesis and all that jazz. But today, if you were to jump up and do a bunch of jumpy jacks, you're not going to get new blood vessels right now. So this is acutely, it's not going to change. Although you can vasodilate them to allow for more contractions. Inflow, cardiac output. So again, that's the heart pumping the blood into the system. We need to change the level of inflow. We need to change the inflow. So we increase cardiac output, which we can do by increasing heart rate or stroke volume. And then outflow is this peripheral blood flow and total vascular conductance. And then that comes back around, so they go down the arteries, through the arterioles, into the capillaries, through the venules, through the veins, back to the heart, and then we get our nice little loop there. And so again, the change in pressure that you would get with peripheral blood flow is basically mean arterial pressure, because if we want to increase blood flow across this vascular bed, what we do is increase blood pressure. Generally, you can decrease venous pressure a little bit, but generally what you're doing is driving this front end of things, the high energy end of things, or changing the conductance through the vascular bed by local vasodilation. Yeah, because the low pressure end of things generally 0. Good. Okay. So, people like me get real jazzed about mean arterial pressure because it's, some would say, a or the major regulated variable in the body. So we really enjoy looking at things like cardiac output and total vascular conductance. So blood pressure, mean arterial pressure I should say, represents the driving force for blood flow through all the organs, again except for the lungs, but that's pulmonary arterial pressure. I tend to glaze over a lot of respiratory stuff you guys will find. Dennis is covering the respiratory lectures, which is really good. This is nice because, I don't know, I think he likes the cardiovascular system. These slides are really good, but he get me with the cardiovascular, Dennis with the respiratory. You'd hate me in respiratory. I'd just be rolling my eyes the whole time. Don't tell him I said that. Okay, so cardiac output is the rate of blood pumped from the heart into the systemic circulation. It's liters per minute. We all know this, right? Yeah. Thank you. And then total vascular conductance is the sum of conductance provided by all the systemic blood vessels. So I don't know how deep into detail we're going to go into this. Again, if you're like super keen, come see me, because this is the kind of stuff like we look at in our lab. Actually, Yasmin's master's thesis looking at local vascular conductance. So when we're talking about total vascular conductance, obviously cardiac output is supplying the like pump end of things to the whole body. And so for calculating mean arterial pressure, it makes sense for using total vascular conductance. But as you know, there's like a ton of vascular beds in the body. So this includes all of them. So this is like splanchnic, renal, all the blood flow that I don't really care about. That we always just look at like the resistance vessels in the muscle. Whatever. Again, this is really turning into a pitch for what I care about. But okay. So, sorry, this is what I was going to say, is that your total vascular conductance to each vascular bed can usually be controlled independently. So, if we're talking about the sympathetic nervous system, I'm getting ahead of myself, but you can control renal sympathetic nerve activity differently from like your muscle sympathetic nerve activity, for instance. So that's why these outflows are all different, because we're decreasing the amount of flow that's going to each individual vascular bed. But then when we're talking about total vascular conductance, again, it's like the sum of all of the conductance. I shall move on. Okay, so the combination of changes in cardiac output, again, your arterial inflow, and total vascular conductance, your arterial outflow, is how the cardiovascular system regulates mean arterial pressure. So if you, I'm definitely stepping on the toes of this. Maybe, let's see how the slide plays out. Oh no, I think that's it. Yeah, nothing's happening. Okay. Wait, that's me, wasn't it? Sorry, I really got no sleep last night. Okay. If you increase cardiac output and maintain total vascular conductance, what's going to happen to blood pressure? You can just yell it. I won't even look at you. Does anyone know? You increase cardiac output without changing total vascular conductance? Increase. Yes, thank you. And I won't do the inverse, because anyway. So, but this is going back again to the inflow-outflow. Oh, he's got his little thing here. If you increase cardiac output without changing conductance, you're going to get an increase in blood pressure. And then obviously the inverse is also true. And in this example, I think he's got the, if we decrease total vascular conductance, which he's showing here as this like narrowing. So this is an increase in resistance. We're decreasing conductance by narrowing the artery, changing the radius of the artery. Remember, that's to the power of 4. So we're increasing resistance a lot based on this tiny decrease, or this actually looks like a pretty big decrease in radius, but you know what I'm talking about. So we're increasing resistance to flow. If you increase resistance to flow, your conductance is going down. So his K got smaller here. See what you did there, Dennis? What happens to outflow? It's going to go down. And then your inflow is bigger than your outflow. And we just talked about this. I just asked you this. We're way ahead of Dennis. Come on, man. What happens to you get an increase in blood pressure? Cool? There's more. Okay. So basically, he's talking about what we were just talking about, that you have an increase in the pressure gradient there. And, like we talked about at the beginning, coming back around, because we've got this imbalance, basically, so we've got all this cardiac output building up, we're pouring water into a balloon that is not able to increase, because we've increased resistance down here, so we can't match it in terms of outflow. So we get this increase in pressure, and then what's going to happen is your cardiac output, like where's it going to go? In a balloon, you would just, I don't know, pop the balloon, I guess, or just start overflowing the top of the balloon or something like that. When you have it at the sink, you know, and it starts coming at the top. But we can't do this because our cardiovascular system is closed off. So eventually your cardiac output is going to decrease and everything's going to stabilize. Does that make sense? Did I explain that confusing? Oh, I got so many nods there. Thanks, guys. Okay. So again, cardiac output can change to compensate for changes in total vascular conductance to preserve or regulate mean arterial pressure. Those are slightly different because sometimes you want to preserve mean arterial pressure. So like if you're like, I don't know, lying watching Netflix or something like that, like generally we don't want massive fluctuations of blood. We don't need massive fluctuations of blood pressure. Sometimes we actually want to change our blood pressure and increase it for a certain reason, like exercise. And so that's where we're either preserving or regulating blood pressure. That's the difference there. But again, because of this equation, if you are increasing one and you want to keep blood pressure the same, you're generally then going to decrease the other to compensate. Good? Good, good? Good. Okay, so what determines blood flow through a vascular bed? So again, flow through a vascular bed is going to depend on the pressure gradient and conductance. And again, conductance is 1 over resistance, and resistance is equal to the length, which is going to change, times the viscosity, which might change if you're like super hydrated, super dehydrated, changing the phase of a menstrual cycle. And then obviously then divided by radius to the power of 4. We also research menstrual cycles, that's why I keep on looking at her. And this is probably not good lecture skills, but anyway. Okay. And this is really hammering home that point. If you decrease the arterial radius by a half, just because of like math with the power of 4, you get a 16-fold increase in resistance / decrease in conductance. So again, very small change in radius, very big change in resistance and conductance. So changes in conductance of a given vascular bed, which occur due to changes in radius, i.e. vasodilation or vasoconstriction. So again, conductance through the vascular bed you get by changing radius. That's the thing that the body's actively changing. Well, I think the body's actually changing is vascular smooth muscle contraction and relaxation, but okay, so sorry. Changes in conductance are the primary way for the cardiovascular system to regulate tissue blood flow to that particular vascular bed. So something's happening in a specific vascular bed and the body goes, okay, we want to increase blood flow. What would cause the body to want to increase blood flow to a vascular bed? Does anyone know? This is a sidebar, but it's also a review for midterm. I heard exercise. Exercise. And what kind of sensory feedback would be telling the brain that you've got an exercising muscle? There's multiple right answers. You can yell them. Or not. I hear whispers, slightly more volume.
Like an increase of CO2 in the blood?
Uh-huh, yeah. So those are your chemoreceptors, your local chemoreceptors, good. Metaboreceptors, oh, sorry, were you going to say metaboreceptors?
Baroreceptors.
Nice, okay, good. Metaboreceptors, what about all of your stretch and your, yeah. So all the receptors that are telling the brain that your body is exercising. So that tells the brain that we need to increase blood flow in a particular vascular bed. So the brain, particularly the brain stem, would be integrating all of those different inputs. I'm winking at you, to cause a change in blood flow, to say, okay, we are exercising, we need to change blood flow to the vascular beds to allow more blood flow through. Okay. So, where are we going with this? Oh yeah, so basically this is just again talking about the change in pressure. We've got the pressure reservoir that's coming up into the arterioles, and then variable resistance outflow tubes. Once again, we can regulate these things on a vascular bed by vascular bed by vascular bed basis. So again, this vascular bed here was getting 750 mils of blood flow, and we can decrease that to get 50 mils. But again, that has to go somewhere if we're keeping blood pressure the same. So you can see it goes up in this vascular bed here. And this is usually what happens. So let's say you're doing something like an isometric hand grip exercise in one arm. What you're doing is redirecting blood flow away from the inactive muscles and towards the active muscles. So you're going to be constricting blood flow. So let's say these are your two arms, numbers 2 and 4 here, and you start doing hand grip exercise in them. And that's a bad example because it's not changing the way I want it to. Anyway, so let's say maybe this one's your active muscle, so you want to increase blood flow here so you can increase conductance through that vessel by increasing the radius. But then that blood flow needs to come from somewhere, so you can either do that through an increase in blood pressure, and or you can do it by constricting the blood vessels in an inactive vascular bed, such as your other arm and your legs, and then that redirects the blood flow because you've got a vasodilation here, a vasoconstriction here, and it pops over to your active arm. Duh? Duh. Okay, so understanding the nature, this is a good title, of the cardiac output, total vascular conductance, mean-arterial pressure relationship. I think this is exactly what I just said. So basically, again, cardiac output, we'll just beat you over the head with this. Cardiac output is our inflow. We have our arterial blood volume. We've got our total vascular conductance. Outflow here. And as I was just saying, vascular conductance can increase in one vascular bed, but blood volume and mean arterial pressure will not drop if the conductance is maintained by a decrease in vascular conductance of other beds. So I was talking about an active muscle versus an inactive muscle. But here we've got your splanchnic blood flow, so like your internal manogemas. Your muscle, this is where all of the resistance vessels live. The resistance vessels that are really, these are the things that change a lot whenever we need to redirect blood flow. Skin, obviously that changes a lot, especially whether you're hot or cold. I think that's our second last lecture or something like that, like thermoregulation. But we can change that a lot. And other, which would include, you know, like the brain blood flow is super tightly regulated. We don't really mess with that. Heart, like cardiac blood flow, all that kind of stuff. So does that make sense? You want to increase blood flow to one area without changing blood pressure, then that means that one of the other vascular beds of the body has compensated for that. I saw a nod, so I'm moving on unless someone wants to stop me. Okay. Oh! I knew that animation was there and I forgot. Again, I didn't get a lot of sleep last night. Sorry, guys. Okay. Oh, we're nearing the end of this. We're gonna have lots of time for review. So, oxygen uptake in the Fick equation. So, we're in kinesiology, so we all care about VO2 max, or VO2, sorry, I should say, so oxygen extraction. So you know that if you want to be a super top athlete, you want your VO2 to go up, and this is the thing that everyone's trying to increase with their training. We're all on board. Okay. So VO2 is calculated by the product of cardiac output and the AVO2 difference. I'm going to say AVO2 difference a bunch of times so that's easier for me to say than this every single time, but the arterial venous oxygen difference. So if you have a big difference, that means you've got a lot of oxygen coming in on the arterial side of things. You manage to extract a lot of that oxygen at the level of the muscle because that's the thing that's using up all of the energy, so through the capillaries. And then you have very little oxygen left over on the venous side, so big AVO2 difference. Small AVO2 difference, you've got however much oxygen coming in on the arterial side, and you did not extract a lot for whatever reason. Inactive muscle, low vascular conductance, that kind of thing. Have you guys learned about that kind of stuff yet? Yeah, okay, good. Well, we have 2 more lectures on it after the cardiovascular, so you're gonna learn it again. Okay. Oh no, I went ahead too far. Okay, sorry. So, so here, x-axis, AVO2 difference across a vascular bed. I actually was texting with Dennis about this morning, and he told me the name for this kind of graph, and I had to Google it. I didn't know what he was talking about. I can't tell you without looking at my phone. But anyway, this graph has a really fun name, and I learned a new word today, which I obviously forgot really quickly afterwards. Okay, so AVO2 difference along the x, cardiac output on the y, and then we have VO2 over here on this y-axis. So basically this graph, like everything's intersecting. So we're predicting VO2, this is our outcome variable here, based on a given level of AVO2 difference in cardiac output. So someone who has really low VO2, so 0.5. A way to have a really, really low VO2 is to have a really low cardiac output. So right here, this person's got a cardiac output of whatever, like 2.5, something like that. That's real low. You're looking at like 5 to 6 as like normal. At rest, sorry, at rest. And then they've got a fairly high AVO2 difference here of 20. But again, that's to compensate for like a crazy low cardiac output. What about someone with a really high VO2? So this can be accomplished with, again, let's go over to sort of like this side of things. So you can add, let's stay up here. So we'll stay at the really high AVO2 difference. So you've got a really high AVO2 difference, so you're extracting a ton of oxygen across that vascular bed. Oh no, I'm getting myself lost in this flipping graph. Let me stay on this person. So this person, as you decrease the oxygen extraction, you would have to increase cardiac output to maintain that level of VO2. The idea, let me skip ahead so that we've got the punchline of this graph here before I get myself real worked up on this. Okay. So you can determine the AVO2 difference based on, like I was saying, like conductance or the oxygen carrying capacity of the arterial blood. So your hemoglobin concentrations, the partial pressure of oxygen in the arterial blood, so again, that's usually 100%, but like if it's gone down for some reason, you increase that. The affinity of hemoglobin for oxygen, which again is affected. Did you guys learn all that about the hemoglobin molecules and they change their configurations and stuff? That's nice. I really always enjoyed that. Temperature and pH in the blood, and then the oxygen dissociation curve, all stuff. Good. So that's going to determine your AVO2 difference. And also, obviously, your muscle oxygen utilization and extraction. So this has to do with, like, if you supply a certain amount of oxygen to the muscle, how much can it take out of it? That's going to have to do with, like, the capillary density, mitochondrial density and function, adequacy of tissue perfusion and diffusion. And all of these things are things that you can increase with training. So if you want to increase your ability to extract oxygen from the blood, again, like, we're going to touch on all this a lot more in those 2 lectures, so we'll kind of skim over this for now. But the idea is, if you want to go from rest with a very kind of like low oxygen extraction to peak exercise, you need to increase your VO2, and you can do that through a change in cardiac output or through a change in the AVO2 difference. So you can, again, it's just like what we were talking about before with the conductance and the cardiac output determining mean arterial pressure. This is the same thing here with the VO2. Cardiac output, again, playing a role here because you can increase cardiac output to compensate for a low AVO2 difference. So on the slide, we've got sort of a healthy, normal person. When they go from rest here to peak exercise, you can see they're increasing their AVO2 difference because they're increasing their extraction. Again, with all of these things, we've talked about like the change in pH in the blood. It's not entirely negative that your blood becomes acidic because this is something that's going to improve the oxygen carrying capacity, that kind of thing. So you have all these mechanisms, and like vasodilation, increasing conductance to the thing. If you're exercising, you're increasing your capillary density, yada, yada, yada. So you can have increase your oxygen extraction here and increase your cardiac output. Boop, boop. Then you look at somebody with heart failure, and you can see when they go from rest to peak exercise, their VO2, I know we're going off the VO2 scale over here for the healthy normal, but their VO2 increases a lot less. Even though they're able to increase in these sort of hypothetical data, increase their AVO2 difference, it's because they're limited in their capacity to increase their cardiac output during an exercise, peak exercise. We're going to talk about why in 1 second. But basically, the thing to take away from this graph is that cardiac output and the AVO2 difference are going to counterbalance each other. Well, not necessarily counterbalance, but they're going to determine what your VO2 is together. Does that make sense? So when we're talking about the determinants of cardiac output, heart rate and stroke volume, I'll be talking about exercise effects, sex effects, my favorite kind of effects, another thing we look at in the lab. So we can look at typical, these are maximal exercise values. So you're looking at these heart rates, and hopefully everyone knows these are not like baseline values. That's a really high heart rate. So maximal exercise values for stroke volume, heart rate, cardiac output for college age, untrained subjects, here and here, and trained endurance athletes here and here. And we've got a male and a female. Okay, so first of all, you can notice that heart rate is the same between all of these people. So when you get someone to max, like peak exercise intensity, generally heart rate's going to be determined by what? Does anyone know what the formula is for what your max heart rate should be? Thank you. Ooh, good volume. I think everyone was saying that whispering. Thank you. I should give bonus marks for volume, but I won't give bonus marks for volume. Don't worry. Okay, so yeah. It's determined by your age, exactly. So there shouldn't be any difference here between the trained and the untrained and the men and the women. Where you do see the change is in the stroke volume, because you're thinking like, okay, if I'm going to train myself, obviously, well, even obviously, but based on what we've been talking about this lecture, you really want to increase your ability to get blood flow to your muscles, thus extract oxygen, yada, yada, yada. What's the one thing you really want to be able to adapt? It'd be really handy to be able to adapt your cardiac output side of things, right? Since that's your like pump that's at the front end, it's that high energy thing that we want to be able to increase. So we can increase it, so don't get bummed out that we're not increasing our peak heart rates. Like it would probably be really dangerous if you could increase your peak heart rate. So what human beings can do is increase their stroke volume. So let's look at the men first. So you have an untrained male who's up around 110 milliliters of blood per heartbeat. So every single time the heart beats, it's pumping out 110 mils of blood. And then you get a trained male whose heart can pump out 180 mils. So you're increasing the stroke volume. We'll talk about how you do that in a second. Same with the female. You get an untrained female, talking about like 90 milliliters per heartbeat. And then a trained female can pump out 125 mLs. And then comparing the sexes, you can see women generally have smaller stroke volumes than men, and this is a size issue. Again, like the female's 50 kilograms here and the male's 70 kilograms, so it's just the size of the heart, predominantly. Okay, and then because of math, remember cardiac output is equal to heart rate times stroke volume. If this is staying constant and stroke volume is changing, then we get these differences in cardiac output. So a peak trained male is going to have the highest cardiac output, a peak trained male. A trained male exercising at peak capacity is going to have the highest cardiac output out of all of these categories. And then this untrained female is going to have the lowest cardiac output. All due to stroke volume. Cool. Okay. Calming ourselves as we get into some autonomic stuff. Okay, so we're just talking about the regulation of heart rate right now, parasympathetic and sympathetic nerve activity. So parasympathetic nervous system nerves contact, actually let me first say this. This is my really fun, I don't know if it's that fun, but my PNS, SNS thing on the heart. I don't know if I developed it or if I stole it from someone, but so I always think of them as like gas pedals and brakes. Does everyone here drive or has driven at some point? Nice. I got full participation on that one. That's great. Okay, so as you know, if you want to speed up, you're going to press on the gas pedal. And if you want to slow down, you can either let off the gas pedal or press the brake, or both. Not both. Here you can do both. In the car, you don't want to do both. So that's sort of the sympathetic and parasympathetic. You want to increase heart rate and increase cardiac output. That's an activation of the sympathetic nervous system. If you want to decrease heart rate, you can do that by pressing on the brake, so activating the parasympathetic nervous system, or by letting off the gas, which is decreasing your sympathetic activity. Is that not the most fun thing you've ever heard? I don't think she's here today, but it's It's not quite as good as the in the door thing. But remember, like in the door coming in, the dorsal. I'm winking at all of you right now. Okay. If you don't know what I'm talking about, go back to that lecture. Okay. So parasympathetic nerves contact both the SA nodes and the AV nodes in the heart. Our pacemaker nodes. When you stimulate the PNS, again, this is like pressing on the brake. That's going to release neurotransmitter acetylcholine to decrease heart rate. So again, press on the brake, heart rate comes down, and that occurs by decreasing the SA and AV node activity. Yeah. So as your parasympathetic increases, heart rate decreases, and vice versa. I think I mentioned this, a couple lectures ago, that we have a really fun enzyme hanging out at the level of the heart, acetylcholine esterase, and that's eating up all the extra acetylcholine. So you press on the parasympathetic nervous system, brake, and you decrease heart rate. PNS, if you want to have a really quick increase in heart rate, a really easy way is to let off that brake. That's where our car analogy falls apart a little bit, because letting off the brake, you just kind of start rolling forward. But with respect to heart rate, as soon as you let off parasympathetic nerve activity of the heart, acetylcholine esterase goes up and eats up all of those acetylcholines that were hanging out inside the synaptic cleft, and you get a really quick increase in heart rate. So anytime heart rate increases really quickly, like within a beat, that's parasympathetic. The sympathetic acts more slowly. It's still fast, but it's more slowly than the parasympathetic. Okay, and then at rest you have PNS tone. So again, our car analogy means that you're kind of like cruising with your foot on the brake, like your mom when she drives. I don't know if your moms drive like that, but my mom is getting older. God, she drives like that. It's really annoying. So you've got kind of your foot on the brake. So there's a level of PNS tone. This is actually real handy because going back to my like saber-toothed tiger kind of analogy, if like one were to like jump into the room right now, you want to have a really quick way of increasing your heart rate. So with the PNS exerting some influence over baseline, all you have to do is let off of that brake. Again, acetylcholine esterase eats up all of those